an outline of what I'm going to talk about. Okay. Some definitions to begin with. I'm going to talk about why global sea level changes, the mechanisms that actually make that happen. Say a bit about how we determine ancient sea level. So looking back into geological time, how do we figure out how sea level changed? And then building from that, talk about that history of global sea level change. You know, what did it actually look like? And then finally, a little bit about tilted continents, Isostacy, and a bit more about relative sea level change, which I'm going to define at the beginning. And the good news is that if that all sounds a bit heavy, there aren't too many numbers and things, so it's not too massively nerdy. And there are quite a few pictures of cats, which I find help in any talk. And these are cats in difficult situations, by the way, so we can see how that progresses through the talk. So let's get started with what actually is sea level. This is the point of sea level in Death Valley in California, by the way, which is if any of you have been there, you know, is quite a lot of it is actually below sea level, but obviously because it's quite a way inland, it's not flooded by the sea. So when we think about sea level, you know, in very general terms, it's just the place where we go, where we paddle, where we get to the sea. Obviously that's the elevation that sea level sits at, and that's probably how most people would think about it if asked to define it. And here's several places around the world where I've been paddling that are very nice. One of the great things about being a geologist is you do get around quite well. We used to get around quite a bit, not so much more recently. And interestingly, though, as soon as we start to sort of look at in a little bit more detail, and particularly when we start looking back into the geological record, what we find out is that it's actually quite a bit more complicated than just one single elevation or point where, you know, land meets sea. There's quite a bit more to it than that. So, for example, I don't know whether any of you recognize this. This is Herculaneum near Naples in Italy. You know, this is the Roman town that was buried along with Pompeii by the eruption of Mount Vesuvius in 79 AD. And the reason that this picture is significant is this line of sort of arches here. These were boat houses that were open out onto the seafront back in Roman times. And the sea now is a good couple of kilometers further away from here, right? Now, so that's a form of sea level change in the sense that this is no longer at sea level. It's, you know, it's no longer at the shoreline at least. So something's happened here to change it. And in this case, it's a volcanic eruption. In Death Valley, it's subsided below sea level and it's still not flooded. In these pictures here, I'll come back to these a little bit later on, we're seeing places back in deep history, geological time that used to be at sea level. So pretty much where you can see this PhD student's feet at one point back in the early Jurassic, that was where sea level was, right? And now it's on the coast in South Wales in a pretty classic outcrop. So as soon as we start to think about it a bit more, we can see that what sea level is and how it's varied through time is quite a bit more complicated, okay? So I've pretty much said all this already, right? I think, you know, you can see the boathouses here, the coastline. I think that's over there somewhere up on this, you know, quite a way inland now. So the seafront has moved quite significantly since 79 AD. So let's just talk about some a quick definition. And when we talk about sea level in technical terms, what do we mean? Well, there's a few different ways that we can talk about it. And the first way, in some ways the simplest way, is this idea of global sea level or Isostacy, okay? So that's a uniformly global change of sea level that may reflect changes in water volume, ocean volume. But when we say eustatic sea level, what we actually mean is the elevation of the sea surface with respect to the center of the earth. That's essentially how it's defined. And the center of the earth is effectively a fixed datum, right? So if we change the amount of water in the oceans, sea level will go up and eustatic sea level will rise. If we decrease the amount of water in the oceans, eustatic sea level would fall, okay? And at the moment, because ice sheets are melting, we're putting more water, well, not us personally, but more water is going into the oceans. And so global sea level, eustatic sea level is rising. Okay, so this is the first thing we tend to think of when we think of sea level. It's global sea level or Isostacy. Okay, So let me show you how we draw this in geological terms when we're talking about sea level change. What we typically do is we use a coastline feature like a delta as kind of a reference point that we can then discuss sea level change around. So this is the Lena River Delta. It's a beautiful example of a river delta. You know, it's a fantastic delta shape. The river's down here feeding out into the Arctic Ocean. You can see this big sort of D-shaped wedge of sediment. And this is obviously is in map view. This is a satellite image. You can see all the channels on the delta top here carrying sediment out to the sea. The shoreline is there where we change from this green to blue color. And this green line here, A to B, is a cross section which is drawn below. So this is now is a cross section down here. And that's the delta top. So that's this line AB. And then when we get out to the point of the shoreline here, the delta dips away underwater on a gradual slope, usually a couple of degrees, maybe a bit less. And then it basically bottoms out onto the seafloor and you get a shape like this. We call these cliniforms, but essentially it's just a wedge of deltaic sediment building out into the sea. And on here, we've got sea level. That's the dashed blue line. And then we've got the center of the earth, not drawn to scale, but just to indicate that it's down there somewhere. And this line then here with the arrows on it is basically global sea level or eustatic sea level. It's the height difference from the sea surface down to the center of the planet, right? So that's what we're using to define eustatic sea level. But we can also define another datum that's a more local datum. So we could take the contact between crystalline basement rocks, which you've probably all seen, things like granites, metamorphic rocks, and overlain by a pile of sediment. So in this case, the sediment deposited by the delta. Take that interface as a datum, and we could say we're going to use that to define another form of sea level, and that is what we refer to as relative sea level. So it's the elevation of the sea surface relative to this local datum surface. Okay, so we've got two datums now. We've got the fixed center of the earth that defines eustatic sea level, and we've got some local datum that defines relative sea level. And I'm just going to show you a couple of cartoons based on this one that explain why we do that and what the significance of it is, right? So if we raise the sea surface globally, it basically looks like this. The water depth goes up. You can see, if we compare, okay, that arrow gets longer as we go between these two diagrams. So the elevation of the sea surface above the center of the earth increases. That's a eustatic sea level rise. But you'll notice we also actually rise this. We also increase this distance from the local datum to sea surface. So when we rise global sea level, we also rise relative sea level, because we're just measuring the sea level rise relative to a different datum. Okay, so global sea level rise and relative sea level rise, they're pretty similar, okay, in this case. But what I can also show you then is a case where it's different. If we keep global sea level constant, okay, and we tilt everything, and I'll come back to why this kind of tilting happens on the surface of the earth. But if we tilt everything, you can see that the shoreline position used to be there. So let me just skip back a couple. The shoreline position was there. And now if we tilt everything, you can see the shoreline has now jumped back to here because this area has subsided, this area is uplifted, and so the sea position has changed. And again, this arrow, this distance from the sea surface to that local datum has also changed. In this case, the distance from the sea surface to the center of the earth hasn't changed. So this is just a relative sea level change. It's not a eustatic change, it's just a relative sea level change. Okay, so tectonic tilting will cause relative sea level change. Some places go up, some places go down, and that will change relative sea level. Some places will flood, some places emerge above sea level. That's basically how it works. Okay, so you can perhaps start to see now why it's useful to have these different definitions, because tectonic processes can change relative sea level locally, even though global sea level isn't changing. Okay. And one final example of that, if we have a fault out here that drops the seafloor, we have a relative sea level rise out here, but actually up here on the other side of the fault, nothing much happens. Okay, so again, relative sea level rise due to local faulting, but in this case, it's a bit more spatially restricted. It only happens over on this down-thrown side of the fault. All right. So this concept's really useful, and I'll mention this a few times as we go through the talk. Now, just to explain what we mean by tectonic then, I'm sure you've heard the term, you probably know what it means, but it's interesting to think about the actual definition of the word. It means of or concerned with the structure of the crust of a planet, Earth, Moon, or Mars, obviously is particularly interesting at the moment because we have the rover there. And it's especially associated with the formation of folds and faults in the crust, right? But any deformation of the crust, including tilting, so faulting, tilting, folding, all of these things, it's all what we refer to as tectonics, okay? But there's a lot of tectonics that goes on also in the oceanic crust, which you can see in this map here. So you can see the ocean ridges in red, you can see the continents and the different colors of oceanic lithosphere here down in the ocean basins. That's color coded by age, and I'll come back in a bit as to why that's important. But processes to do with how ocean basins form and spreading centers and, you know, the mid-Atlantic ridge, the East Pacific rise, that again also it's all tectonics. Okay, so anything to do with these ridges and subduction and all that plate, it's all the kind of tectonic processes that might also affect sea level. And I'm going to talk a bit about how actually that all works. How do tectonic processes influence not just relative sea level as we just saw, but also global sea level? And we can make plots like this that actually explain in slightly more technical terms how tectonic processes and global sea level processes added together form relative sea level. But we won't dwell on this, right? There's all sorts of things that you can do that are ways to analyze these different processes. And then one final point in this section, and this comes back to the Herculaneum Vesuvius point, right? If we had a shoreline here and then the delta continues to build out, the shoreline will move, right? Because the river is feeding sediment into the sea and the shoreline builds out seawards. So this is not, though, any form of sea level change. It moves the shoreline, but sea level, in fact, both relative sea level and eustatic sea level might stay constant. So that example I showed you from Herculaneum is probably just building out of the coastline due to deposition of volcanic material. It may not actually be a sea level change, even though it's hard to tell that for sure because the shoreline's moved. So you can't really tell whether it's changed elevation or whether it's just changed horizontal position. So you start to get a sense now that maybe this is quite, you know, involved. There's quite a lot that we need to try and understand here to get a full understanding of what sea level is doing. And finally, it's also possible that if we're pouring enough sediment in through the rivers to a delta area, even though sea level does go up, so it was down here, now it's up there, so it's risen by this little height difference here. Even if sea level does go up, the shoreline might still continue to build out because there's enough sediment to maintain that happening. Okay, so you're probably getting a sense now that this is a bit more involved than just, you know, going to the beach and taking your shoes off and dipping your feet into the sea there. That sea level is actually quite a complicated thing to try and understand the history of through time. So there you go. I think I've said all that, so I won't dwell on it. So why does global sea level change then? Let's talk about some of the mechanisms, and hope we don't get stuck in any of the topics like this. Rather unfortunate. Yeah, I can't imagine that would be a happy. I'm sure it was happy to be rescued, but I would be cautious about going. Cats get very bad tempered when they feel humiliated. I know this from experience. So anyway, why does global sea level change? There are two basic reasons why global sea level changes. Okay, it's either to do with the amount of water in the ocean basins, right? Or it's to do with the volume of those ocean basins. And here's a list of things that control those two things. So if we're talking about the ocean basin volume, that changes because of the overall thermal age of the lithosphere, of the oceanic lithosphere, the rate at which ocean crust is formed at spreading centers, and this thing called dynamic topography that I'll explain. So I'm going to go through those things and explain them quickly. In terms of ocean water volume, so how much water is actually in the ocean basins, that's mostly controlled essentially by climate. Okay, and I'll explain why that is in a second, right? And then talk about some of these numbers down here, which are related to how much sea level rise there would be if ice sheets melted. Okay, so let's go through the climate controls first. So seawater temperature. If you increase the average temperature of the seawater in the ocean basins, the water expands, because water expands when it warms, right? So you increase the temperature, the water expands. That increases the volume of water in the ocean basins and global sea level goes up. So this is what has been happening over the last 100 years or so, as global temperatures have gradually risen. So the ocean basins, the water in the oceans has been heating up, expanding, and sea level has risen. And this typically happens centimeters to a few meters change over hundreds to thousands of years. So actually, compared to some of the other things we're going to talk about, it's quite slow, but it's not insignificant, right? I mean, there has been significant sea level rise of several centimeters, which doesn't sound much unless you live on a sea cliff that's being pounded by storm waves. Then it can make a difference. So several centimeters over the last 100 years or so. So that's seawater temperature. The thing, aside from temperature, is how much water is stored on the continents. And it can be stored in two different ways, basically. It can be stored as lakes and groundwater. And that there's some flux from lakes and groundwater back into the sea, and obviously rainfall brings it back from the sea into those stores. So that changes over time, the balance between the ocean water in the oceans and in those two lake and groundwater stores. But again, the rate is actually pretty slow. So the really big thing that can potentially change global sea level very rapidly are ice sheets. So ice sheets can store a huge amount of water on land. Right. So, for example, the East Antarctic ice sheet is the biggest single ice sheet on Earth at the moment. If that were to melt, we would raise global sea level by around 52 meters. Even smaller ice sheets, the Greenland ice sheet, I mean, it's pretty big if you look at Greenland, but globally, it's one of the smaller ones. That would raise global sea level by 7.3 meters. So obviously, what's happened in the last 20 million years or so, when those ice sheets have formed, is sea level has fallen by this amount. Now that those ice sheets are melting, and let's hope to goodness they don't melt too quickly, because we're going to be in trouble if they do, but global sea level is going to rise by that same amount and go back to how it was when there were no ice sheets. If they all melted, we'd have a total sea level rise of about 65 meters. And we'll come back to this, but if you think about how many coastal cities we have around the world, some of these sea level rises, if we let them happen because of global warming, it's going to be pretty substantial problem. So continental ice caps are a big driver of global sea level change when they form and when they melt. And just very briefly, in the past, before humans started influencing things so widely, most of those cycles of ice sheet formation, melting and forming, were driven by fluctuations in the Earth's orbit around the sun, which subtly but actually importantly changed the amount of solar radiation hitting the planet, warmed it up, cooled it down. I mean, it's quite a complicated effect, actually, as it turns out, but we're pretty sure that was the driving force. Now, there's no doubt humans have taken over as the main reason for climate change. We've kind of, had such an influence on the Earth that we've kind of outpaced these slower orbital forcing changes. Okay, now tectonics, let's talk about this quickly. That was all about the amount of water in the ocean basins. Now let's talk about what changes the volume of the ocean basins. So you probably all know from plate tectonics, new oceanic lithosphere gets created at spreading centers. So here's the mid-Atlantic ridge that's a spreading center, runs down the center of the Atlantic Ocean and up into the Arctic Ocean. The geometry and the speed, well, the speed of spreading, let's talk about that first of all, on this ridge. So how fast the plates pull apart at that spreading center has a big control on the height of the ridge, how elevated it is above the lowest points in the ocean. And that has a big control on ocean volume. So a fast spreading ridge tends to be shallower, and it makes the whole ocean basin shallower, and that displaces water up onto the continents, causes global sea level rise, simply because it reduces the volume of the ocean basin. In contrast, a slow spreading mid-oceanic ridge creates a deeper ocean basin, bigger volume, more capacity to store water, global sea level drops. Okay, so through time, as these processes, as the age of the lithosphere and the spreading center and the rate of spreading changes, that changes ocean volumes and sea level goes up and down. So the age is important because the youngest hot oceanic lithosphere is very buoyant, it sticks up. The much older, colder, denser oceanic lithosphere sinks, right? So if you look over in the West Pacific, where the oceanic lithosphere is very old, it's Jurassic in age, lower Cretaceous Jurassic, that's a very deep bit of ocean there, right? So you've got much more potential to store water if all of the ocean is older. If all of the oceanic crust is quite young, the ocean basins will be shallower, more water will be displaced onto the surface. So we've got these two things. We've got rate of spreading and age distribution of the lithosphere. They control the volumes of the ocean basins, and therefore how much water will fit in them, and therefore how much water is displaced onto the continents, and that's global sea level. Okay, and these rates are actually pretty slow, okay, but we're really making good progress in understanding exactly how the history of plate tectonics has influenced that sea level history back through time, right? So this is some quite recent research. There are more recent versions of this by a team from Australia who do plate modeling and by extension model global sea level and how it's changed, right? So plate tectonics and sea level are inextricably connected, okay? And one final point, and I'll come back to this, we also have to consider what goes on inside the Earth, because convection inside the mantle forces the crust up and down over time. This is what we refer to as dynamic topography. So this is a beautiful image from a computer model produced by the Swiss university in Zurich. And what you can see here is plumes of hot material rising up from this ball here is the core. The sort of open part of the globe here is the mantle, and the crust is this outer layer out here, right? Crust in the lithosphere. So you can see this is a descending slab of oceanic lithosphere that's coming down, and it's being laid out on top of the core. Here we've got big masses of hot material rising up through the mantle and hitting the base of the lithosphere. So this is just a computer model, but it's actually a pretty realistic representation of what happens inside the Earth. So as these plumes go up, they basically push the surface of the Earth up above them. As slabs, subducting slabs like this come down, they drag the surface of Earth down above them, right? So the surface is going up and down because of this convection effect. And if the surface goes up and down, we get either elevated areas or depressed areas. It changes the volume of the ocean basins, causes global sea level, but it can also cause relative sea level changes, because in here, for example, if the coast of Africa gets pushed up because there's a plume coming up beneath it, that's going to cause local or regional relative sea level fall. All right. So there's a lot going on with sea level. Okay. It's a complicated business, several different processes, several different controls. And that's essentially a summary of how all the different processes happen. Okay. So how do we figure out ancient sea level? Right, and we're going to get back to some more traditional geology now. If you're feeling a bit like this, Kat, don't worry. We're gonna actually look at some pictures of rocks in a moment. First of all, though, the last 100 years or so of sea level change, you can see that we've had a rise of about 200 millimeters, about 20 centimeters over the last 100 years, and that's mostly been due to this thermal effect. The ice, the water in the ocean basins has been warming up, it's thermally expanded, and that's caused sea level to rise. And this is pretty much direct measurement. Okay, that's the point really of showing this graph here. For the last 100 years, we've been able to measure it directly via tidal gauges. And most recently, this red part is by satellite altimetry. We've now got a network of satellites that bounce lasers and radar off the surface of the Earth and use that to measure sea level. So we can do it very accurately now. The tidal gauge data was a bit more noisy, you know, a bit more uncertainty, but this is what's happened over the last 100 years. But what about back into geological deep time? How do we figure that out? Well, we look at rocks, right? So these are two places that I already showed you pictures of. This is South Wales, an early Jurassic shoreline. So we've basically got Jurassic limestone onlapping, or so in horizontal contact with an inclined surface. This is an erosion surface on top of the Carboniferous limestone. You must all have seen a lot of Carboniferous limestone. It's one of the main, you know, rock units that outcrops over islands. So I guess you've seen lots of it in the field. And this is the Variscan Unconformity, which I think you've probably also seen in places. So that's a pretty direct marker of sea level. Essentially, sea level rose and the sediment onlapped along this surface. At some point, it was at the student's feet, and over here, it was basically, it got to above his head. And you can see, you can trace these bedding surfaces in the Jurassic limestone that essentially mark pretty much where sea level would have been. Okay, and here's another slightly more subtle shoreline deposit from the Miocene of Spain. Basically, here's like a big mass of jumbled up rocks. So this was a rocky shoreline back in Miocene times. There's a sandstone immediately above it. Okay, this is sandstone. Below it, there's a schist, phyllite schist, which is, you know, metamorphic rocks. So here you had basically mountains right down into the sea, and they were subsiding. Tectonic subsidence was causing sea level to rise, and the sand banked up against like a rocky shoreline. Okay, so when we see outcrops like that, we can say that's where sea level was in the Miocene, in the lower Jurassic, you know, whatever the time is. And similarly for rocks all over the world, there are examples of this. So this is an example from the late Cretaceous of Utah, where there's beautiful delta deposits that we can use to reconstruct the sea level history there. And if you put all of those things, well, actually, I've talked about this. I won't go on about it more, but you can see that's a more graphical representation of what I was just describing. Here's another source of data, right, that we can use to reconstruct sea level. So we can put together the information from this to reconstruct sea level, and we do that using some of the same principles that I talked about in that previous diagram. So this is an old river delta that's buried under the surface. It says offshore Namibia, but I think this might actually be the North Sea, slightly less exotic, but it doesn't matter where it is, the principle's the same. And you can see where it goes from flat to dipping. That's the same as this diagram I showed you earlier. Those dot positions are where the shoreline was at some point back in geological time. So if we connect those up, we essentially get a reconstructed history of how sea level, or how the shoreline position at least, has changed. And from that, we can go about reconstructing some of the sea level history. So this is called a shoreline trajectory. It's a key technique that we use to figure out what sea level was in the past. And we can do similar things, not with river deltas, but with carbonate platforms, which are big constructions of limestone produced by reefs and other rock building organisms. And again, here's a modern one. This is the Caicos Islands in British West Indies. You can see there's the red here is above sea level, so that those are islands. There's a really lovely, probably great place to swim if you don't mind a few sharks, lagoon here, and the darker blue is deeper water that's off the edges of the carbonate platform. And you can see what that looks like in cross sections. This is a seismic line. I don't know whether you know about seismic data, but it's like ultrasound images of the Earth's crust, right? So you bounce sound down and into the crust from some sort of source like an air gun, and then record how long it takes to get reflected back to the surface. And doing that, you can build an image like this. It's like an ultrasound cross section. So these are all layers of limestone. These are layers of mud and sand, and you can see the shape of the carbonate platform in there. And because we know that this lagoon surface on top of platforms like this is very shallow, basically each of these horizontal reflections, seismic reflections in here, is basically telling us what sea level was back, in this case again, in the Oligocene to Miocene, so about between 30 and 10 million years ago, right? So these are fantastic for reconstructing past sea level history. And here's an even more stunning example where you can see all the layers have been tilted and then new layers have been deposited on top. You can see there are pinnacle reefs here. So what's essentially happened is the platform has kind of built out into the sea very rapidly and then been forced back to retreat until eventually it's drowned. And these pinnacle reefs are the last bits of the carbonate platform trying to keep its head up, well, its head at near sea level, right before it was finally drowned and went into deeper, darker water where the corals and so on can no longer grow. So again, this a seismic section like this, and this is from Southeast Asia, from a basin that has actually gone down and subsided and tilted very rapidly because of tectonics. Very interesting story. But we can reconstruct the sea level history from a seismic image like this. Okay, and then I think finally, there's another way that we use oxygen isotopes, essentially two different isotopes of oxygen that occur in different ratios in seawater, depending on how much ice is frozen on land. That's the essence of it. So if we measure that isotopic signature preserved in samples of ancient seawater, which we find in rocks, okay, because seawater gets into the rocks, and if we analyze the rocks carefully, we can extract that seawater from, you know, even 100 million years ago and analyze its isotopic content, and we can reconstruct from that the isotopic ratio, ice volume, and get a proxy for sea level. So it's another way that that sea level is determined. Okay, so there's several different techniques that we can use, from rocks, good old-fashioned outcrops, to more advanced geochemistry, and lots of use of seismic images to try and figure out what sea level did in the past. So what do we get then when we actually look at that sea level history through time? We get lots of squiggly lines, basically. And this is one of the first, or the most famous early sea level curves, produced by a guy called Hack back in 1988 and 1989. And what we're seeing there is time on the x-axis, and sea level is this squiggly line here. So I think this side is high, this side is low. So there's a low sea level there, there's a high sea level there. And if you look at the trend through time, back in the Cretaceous, sea level here was high, and according to Hack at least, and his sea level curve, it's gradually dropped down to the present day. And this is probably pretty accurate, because we know that what's happened since the late Cretaceous is the Earth has cooled up until very recently, and ice sheets have formed, and they've caused the water volume in the ocean basins to drop. Sea level has dropped. Okay, so this is the Hack curve. But there are lots of other curves, because people like making sea level curves, and they're, you know, quite a useful thing. So Hack himself has compared his curve with several others. And this plot always makes me smile, because it's one of those things in geology that you need to take with a little bit of a pinch of salt. We know certain things about the history of sea level, but if you look at those different curves, the key thing is they're quite different, right? So each of these lines is a curve produced by a different group of researchers. And I think if I was those researchers, I'd be thinking, well, hang on, why is my curve so much different from their curve? Are we all, I mean, it's worrying, isn't it, that they're so different, right? So what this says to me is there's still quite a lot of uncertainty about the details of exactly how global sea level has changed through deep geological time. We're talking about the last 500 million years now, mind you, so it's a long time, right? Difficult to be certain about anything happening 500 million years ago. But the curves are different, and that's a really important takeaway point. Here's one of the most recent sea level curves, and this is one of the ones that's been constructed very carefully, actually, in fairness to the authors, and there's a good estimate of uncertainty in here as well. So it's a bit, some of the others are a little bit more gung-ho, let's say. This one is a little bit more careful. So this is the sea level curve that I would use. But even this, there are issues with. What you can see, though, is that there has been a drop from a high sea level, so yeah, in this case, high is down the bottom, low is at the top. You can see again, sea level has dropped reasonably consistently through from the late Cretaceous to present. And you can also see that it began to change very rapidly. Sea level is going up and down very quickly on this red part of the line. And that's because the ice sheets have formed in the Northern Hemisphere and in Antarctica, and they're waxing and waning, melting and reforming, and that's driving big oscillations in sea level. And this sea level curve was put together by a guy called Ken Miller from a US university. And then finally, here's the from this chap I mentioned already, Dietmar Muller et al. And I won't go into that, but basically they use a different method, different squiggles, and you know, they're also actually in the process of comparing the different curves. It's at the point where people are trying to figure out why they're different. I mean, I think that would be the summary of it. And I think try to reach some sort of consensus about what the detailed history of sea level change through deep time has been. Right now, one thing that we need to say is, if you look at the rates of change on these curves, we get things like a 230 meter drop from 100 million years ago to present. And that gives us 0.02 meters per 10,000 kiloyears. Okay. And we can get some slightly higher rates than that, depending on where on the curves we look. But basically, we know from this modern rate, 20 centimeters in 100 years, that's much faster than any of the rates that we're actually reconstructing from past deep time sea level curves, right? So we know that our warming of the planet has already produced a faster sea level rise than is typical through most of Earth history, all right? But none of these are the really fast rates. So let's now look at the fastest rates that global sea level has changed at. Probably the best known example of really rapid sea level change occurred between 20,000 years ago and about 8,000 years ago. And this was because the Antarctic ice sheet got smaller, but most significantly, big ice sheets on Northern Europe and North America and all across the Arctic basically melted. And in doing so, and they left remnants. So the Greenland ice sheet is the remnant of that much bigger ice sheet. But, you know, most of Ireland was covered in ice. Most of Britain was covered in ice at the last glacial maximum 20,000 years ago. It melted and it drove a very, very rapid rate of relative sea level, of global sea level rise, 125 meters in 10,000 years, right? Now that is really fast. Okay, even compared to that rate of 20 millimeters that we were looking at before, it's fast. So what this is leading on to is that if we continue to let global warming carry on, global climate change go on unchecked, and the oceans warm up and the atmosphere warms up enough that the ice sheets become unstable and really begin to melt rapidly, if something like this happens, then we're putting ourselves in really serious danger. I mean, climate change is bad enough, but climate change plus big sea level changes is going to be really difficult for us to manage as a society. So, you know, this is one of the key warnings, I think, from anthropogenic global warming. We need to really be careful how much we destabilize ice sheets, because they really do start to melt. Our coastal cities are threatened by really, you know, well, they how long they would survive under that scenario, we don't know, but in 100 years time, they would be probably, lots of them would be flooded. Okay, so that's how global sea level has varied over geological time, and a little bit about how it might vary in the future if we don't take heed of some of these warnings about, you know, trying to make sure ice sheets don't melt. And then finally, a little bit about tilted continents, isostasy, back to relative sea level change. So isostasy is this principle that the Earth's crust floats according to its density on the viscous mantle beneath it, right? And it's a bit like putting blocks of wood into a bath. The thicker blocks of wood would have a keel beneath the surface, and they'd float a little bit higher because they're you know, they're compensated by that keel. And you can produce a similar kind of effect by density. So essentially, if you produce topography at the Earth's surface, you have to have a matching route of material beneath some datum that's floating in order to support that topography. That's kind of the principle of isostasy, right? So what this means, though, is it isn't just about topography. If you put something like ice on top of the Earth's crust, you force it to float lower on the mantle beneath, right? So you cause subsidence. And when you remove that ice, everything over the space of a few thousand years pops back up. So it's floating. You forced it to float lower because there's a weight of ice on top of it. And when you remove the ice, it pops back up. Okay, so that's essentially isostasy. Why is that significant to see? Oh, that's two different models for how it works that I just kind of mentioned very briefly. We don't need to dwell on that. So here's a picture of what I was just describing, an ice sheet. The ice sheet has gone, you get uplift here. Now remember, uplift and subsidence cause sea level change, relative sea level change, because if you depress an area below sea level, chances are, if it's not too far from the coast, at least it can be flooded. All right. So the reason this is significant actually for lots of places around the world, this isostatic effect, is particularly in the Northern Hemisphere. So in Europe, in North America, there used to be a big ice sheet. And actually, as I was just mentioning, it's melted. And aside from rising global sea level, the other effect this has had is that it's tilted places like the British Isles up in a rebound effect, so that Scotland, northwest Scotland, is still going up slowly as the final stages of that isostatic rebound, and southeast England is basically going down. So there's a big north to south tilt of the British Isles going on, and the numbers aren't included here for Ireland, but I'm pretty much the same thing is happening, probably slightly less extreme rates because it's not quite so far north, the northern tip of Ireland. Okay, so this is an isostatic effect that's causing relative sea level change even now, and this is the reason, or one of the reasons, why southeast England is going down. So London is, has increased flood risk through time, irrespective of global sea level. And it's why you've got so many raised beaches all along the coastline of northwest Scotland, right? Because everything's being uplifted due to this isostatic effect. So big relative sea level changes. You can even see it in the outcrop pattern through England and Scotland. Much older rocks in the northwest, much younger rocks in the southeast. And that's essentially because the whole of the British Isles is tilted up to the northwest, right? Now, this is partly that isostatic effect, but it's partly also probably something else. And that's the next thing I'm just going to go on to talk about. It indicates a much longer term tilting that predates any ice formation over Britain, right? So what's that effect all about? That is also something that we see reflected in other continents. So if you go to Southwest USA, you'll see lots of beautiful stratigraphy. In the Grand Canyon, we've got a succession there from the Neoproterozoic through to the Permian. If you go to places in Utah, you can see the most spectacular Aeolian sand dune rocks, all this layering. It is all slightly tilted. None of it is completely flat. Okay, and there's a few different reasons for that, but one reason is because of this tectonic effect that I'm about to explain. So there's a bit more detail here about all that sort of stratigraphy that covers North America. There's several different intervals of deposition separated by unconformities. For a long time, people thought that was just due to global sea level changes, and we now know it's more complicated. It's due also to tectonic effects. Okay, so some unexpected animation there. And here's some of the tilted strata. If you've ever been to Southwest USA and been to national parks like Zion and Bryce, you'll have seen these beautiful cross sections. I just love these bits of geological art. They're gorgeous, but they show really nicely the succession of cratonic rocks there, the rocks formed in the interior of the continent that are all tilted one way or another, right? And we can also look at the distribution of the different ages of rocks through time, and they move around. The places where they're being deposited shift through time, which again is indicating that there's something going on with the continent tilting it to and fro. It's not just a flat surface through geological time. It's more complicated. So what is causing that is this thing that I showed you before, this dynamic topography effect. Okay, so convection in the Earth's interior, in the mantle, pushes the surface of the Earth up or sucks and drags it down over a subduction zone. And that is causing these really long wavelength, long distance tilting effects that I think we can see in the British Isles, right? I don't think that's really proven, but I think it's a pretty good hypothesis that at least some of the tilting between northwest Scotland and southeast England is of an effect related to this. We can pretty definitely see it in across North America. Okay, these long distance tilting of rocks, and it's essentially this tilting through time. So this pattern changes through time. This is how it looks now. In the geological past, where it's now red, it probably used to be blue. And if you think about that for a moment, if this has gone up over this red blob, in 100 million years, that's replaced by a blue blob, basically you're getting tilting of the continents to and fro through time. And that's driving relative sea level change. It's causing shorelines to move around. It's tilting all the rocks. It's producing some of the effects that we've been talking about. And here's just a slightly more detailed view of that. A lot of that tilting in the case of North America happens because the Pacific oceanic lithosphere is being subducted beneath North America. So beneath California and the Caribbean, this, what was referred to as the Farallon slab, is sinking below North America. So North America's up here, the Farallon slab is sinking below it, and it's causing things to tilt in North America. And it's part of the reason why we can see all these tilted layers of rock in, you know, Utah and even Kansas, actually, quite over big parts of North America. Okay, so tilted continents also cause relative sea level change. All right, and I've worked on this for a long time now, since I was a postdoc in Caltech, and it still blows my mind that the continents can tilt in this way over geological time periods. They're just not stable things. If you wait long enough, things will change, things will tilt, sea level will rise, you know, you'll get relative sea level rise, and where you once had dry land, you'll have perhaps a big interior seaway right through the middle of a continent. That's what's happened in North America in the past, right? So this is over geological time periods, this is a really interesting and significant effect. Okay, so let me just summarize all that then. Sea level change is surprisingly complicated. If you've been listening to me for, the best 50 minutes, you'll probably appreciate that it certainly is. It occurs due to several different processes. Some of them are climatic, some of them are tectonic, some are fast, some are slow, and some are dangerously fast. And those ones related to melting ice, we need to be really careful of. Reconstructing sea level histories back through geological time is tricky. All those curves look different, but there are things that they have in common that we understand pretty well. Global sea level was high in the late Cretaceous. It's lower now. I mean, that's pretty much an established fact. Lots of evidence for that. And then finally here, deep earth processes affect the surface of the earth. So it's not just about water volumes in the ocean basins. It's not just about even spreading ridges in the ocean basins. It's also about what happens deep down inside the earth in terms of convection patterns, rising plumes, subducting slabs. All of that also has an impact on sea level and the rocks that form at the surface. And then just one final time, melting ice sheets are bad news, not fake news. I think there's still there isn't really any debate about climate change anymore, to be honest, but there are still people who do want to try and argue that this is not really happening. And I think we have to accept now that it really is. The evidence is overwhelming, and if we let it continue without doing anything for too long, ice sheets become unstable. We're making really serious problems for ourselves. And finally, because that's quite a heavy point to end on, this is my favorite cat picture, which I don't think really needs any explanation, but this is the kind of thing that cats do. They've definitely got a sense of humor. Okay, so I'll stop there, and happy for any questions if anybody still has any energy left for asking questions.